Hey everyone, I'm going to run through the answers to the Unit 9 Worksheet 1 on impulse and momentum. This is a topic that can be a little tricky up front, but as you go through examples and sort of get the way in which to think about these questions, it comes a little bit easier, and the equations are pretty straightforward. So just as a real quick thing, I'm just going to write down what my equations are. I have P equals mv, and I know that the average force is equal to the change in momentum over time, and that change in momentum is what we call impulse. In the first question, it asks us to consider some scenarios. So question 1a, why are padded dashboards safer? That padding, what it does, it's not going to change the fact that your change in momentum, and remember momentum is mass times velocity, your change in momentum in a car accident is going to be the same no matter what. Whether you hit a brick wall or hit a big giant pillow or just don't hit anything and hit the brakes, your change in momentum in all of those cases is exactly the same. The impulse is exactly the same. What's different is the time it takes. When you hit the brakes, you're slowly slowing down at a rate that doesn't apply that much force to you. Yes, you might feel yourself being pushed around in the vehicle, but that's certainly different than the case of being in a car accident where you slow down very, very quickly. The padding on the dashboards, therefore, is all about increasing this value of time. If the impulse is always going to be the same, all you can really hope for is stretching out that time just a teensy bit. Even a few milliseconds might double the time that it takes for you to stop, and therefore cut the force down in half. Letter B, why are nylon ropes which stretch considerably under stress favored by mountain climbers? So if you have a situation as a mountain climber where you fall for any distance and then catch yourself on a rope that doesn't have any give is very similarly going to have a very small contact time and therefore a very large force all at once. Whereas if you can stretch that force out over, that's a funny pun, stretch that out over a longer time period as the rope is stretching, then that's going to be less average force, the same total amount of impulse, but stretched out over a longer period of time. Why is it preferred that railroad cars loosely coupled with slack between the cars? Same situation. By having some slack, by having some give between them, what you're enabling is that contact time to be a little bit larger and the force doesn't spike quite as high. Letter D, why is it difficult for a firefighter to hold a hose that ejects large amounts of high-speed water? Yeah, this is a momentum question, right? So if you're holding a hose and all of a sudden that hose is propelling tons of water forwards, giving it forwards momentum, the hose itself, as the water is being shot forward, the hose is going to be pushed backwards, and potentially you along with it are going to be pushed in the opposite direction. And this actually comes down to the conservation of momentum, that as objects interact, the water is only able to be pushed forward because of the pressure of the water behind it. And as that water is pushed forward, the hose and the remaining water inside of that hose is simultaneously pushed backwards, which is why you can see, videos of these hoses that kind of get away from a person and then they go whipping wildly throughout the air. And that's because as it's expelling that, there's a equal and opposite force and an equal and opposite momenta, that is change in momentum, that is given to the other side of that interaction. So those are some conceptual questions, and good ones, I think, to really set the stage for how we think about momentum. Number 2, two objects A and B have identical velocities. Okay, so the same velocity. Object A has 3 times as much mass, though. Compare the momentum. So if we look at this, if we have object A and object B, object A has momentum of 3 times the mass times velocity. Object B has momentum of just 1 mass times velocity, and therefore we can see why it is that object A is going to have 3 times as much momentum as object B, since momentum is just straightforward mass times velocity. For the next question, number 3, it asks the same thing for new masses C and D, which have equal mass, but C has twice the velocity. So again, the momentum is 1 unit of mass, but twice the velocity. And for object D, it's 1 unit of mass and 1 unit of velocity. And we can see here that object C is going to have twice as much momentum. Whatever mass and velocity are for these two objects, it doesn't really matter for the way the question's worded. We know that object C is going to have twice as much momentum as object D, just by virtue of the fact that it's moving twice as quickly. Question number 4 asks about a Mack truck and a Geo. So a Mack truck being big giant truck, a Geo being a relatively small kind of car. They're traveling at equal speeds and they have a head-on collision, so smack into each other. Which vehicle is going to experience the greatest force? If we look at force as it pertains to momentum, force is the change in momentum over time. If two cars are colliding head-on, I'm going to assume that they're experiencing the same time of the collision, right? That the crunching or whatever's going to happen is going to be the same amount of time for both of them as they continue to collide, and you can't really have one disappear or stop colliding while the other's still being acted upon. So same time. And then the surprising thing might be that they're going to experience the same change in momentum. That because of the conservation of momentum, it doesn't matter which one is going faster or which one's bigger, they're both going to experience the same change in momentum. And that's because momentum is always conserved. So whatever the total momentum was in one direction of that system and the total momentum was of the other direction in that system, because when these two objects collide, momentum needs to be conserved, both objects are going to experience the same change in momentum. And I should say the same magnitude in the change in momentum. One will be in one direction, one will be in the other direction. So because of that, they have the same impulse and they have the same amount of time. Therefore, it's going to be the same force of impact. And that surprises people, right? Because you imagine that a person in the tiny car is going to be in a very different situation than the person in a giant truck, right? A person cruising along in a big enough truck is going to be like boom, boom, not even notice anything. But what's really happening is the force is being split between these two things. And remember, Newton's third law tells us for every action, equal and opposite reaction. So the force will be the same. Now there is a difference. I'm not saying that you should go out and just ride your tricycle on the highway. Don't worry about it. It's the same force no matter what. Obviously there's something different about these systems, but it's not the force. For the second one, which one's going to have the greatest change momentum? I already gave that away. They're both going to have the same change in momentum. Okay? So it's not the force. It's not the momentum. Letter C, which one's going to experience the largest or greatest acceleration? The forces will both be the same. But remember, force equals mass times acceleration. If you're in the Mack truck, you as a system, you plus the truck that is containing you, has a massive mass. And so for the truck, let's see, Mack truck, it would look like this. Force equals big giant mass, little acceleration. Meanwhile, for the Geo, force equals littler mass, bigger acceleration. So the acceleration experienced by those individuals is going to be very different because the car, the Geo, while it experiences the same force and the same momentum change, it's going to experience a greater acceleration because the force that's being delivered to that car and its passenger is spread out over a much smaller mass and therefore can lead to a much greater acceleration. And that acceleration is the reason why you don't ride a tricycle on the highway, because if you got struck while you're riding a tricycle, it's just sort of a more exaggerated version of this example where because you have such a small mass, it's going to be a huge acceleration, and that acceleration is really what becomes the potentially deadly thing, as that's a larger amount of force that's being applied to you specifically, the human. You're not shielded by as much car mass. Okay, cool. So the next question, now we're getting into some actual numerical ones, is while being thrown, a net force of 132 acts on a baseball for a period of 4.5 times 10 to the negative second seconds. If that sounds like an unrealistic amount of time, I encourage you to check out some of the videos of various sports balls and being whacked by various sports ball implements. The collision is actually very, very brief. I mean, just think about like a baseball game, ball's coming in, batter hits. It's not like batter's hitting the ball, boom, 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 boom. No, it's just like it's gone, right? Super, super tiny amount of time. So just writing out the variables that I'm given, I have 132 newtons of force, I have a value of time that is 4.5 e negative 2, and I'm asked for the magnitude of the change in momentum. Looking at this equation, I've got 132, I've got 4.5 e to the negative second. I can solve for that. And so if I rearrange this for the change in momentum, I get 132 multiplied by 4.5 e negative 2, and that's going to be some number. Hold, please. 132 times 4.5 e negative 2. I get a value of 5.9 kilogram meters per second. Now, that could be negative, could be positive. It just depends on our reference point. You know, are we considering the direction that the ball is being hit positive? If so, then this is a positive value. If we consider it to be negative, then it's a negative value. It doesn't really matter. The magnitude would be 5.9. Of course, it does matter if we're continuing this problem and thinking about how you know, the ball experiences this change in momentum in the forward direction, and therefore the bat experiences the same change in momentum in the negative direction. That's a little bit of a different problem. The next one, if the initial speed of the baseball is 0, then what will its speed be when it leaves the pitcher's hand? Oh yeah, I misspoke. It's not the bat hitting in this problem, it's the pitcher throwing it, right? Yeah. All right, whatever. So for this, we're solving for then what is the velocity of the ball. So if the ball has a change in momentum of 5.9, and I know that momentum is equal to mass times velocity, then I know that the momentum of 5.9 is going to be equal to the ball's mass, which is 0.14 kilograms. That's given to me in the problem, multiplied by some velocity, and I'm going to solve for that velocity. So it's just 5.9 divided by 0.14, and I get about 42 meters per second. Pretty quick. I don't know, somewhere 80 miles per hour. Pretty quick. Good. Number 7, when the batter now hits the baseball, the force is, I'm just going to continue this, the force is now 1,320 newtons, opposite to the ball's direction of its initial motion. And it acts on the ball for a total time of 9.0 e negative 3, so a very short period of time. And right away I can see that, like we did previously, I can find what is the change in momentum on the ball due to the bat striking it. I can find that by multiplying these two things together. So 1,320 multiplied by 9 times 10 to the negative third, and I get about 12 kilogram meters per second. If I'm sticking to 2 sig figs, I have 12. Okay? Now, here's where we have to be careful. The change in momentum is going to be 12 in the direction that the bat is hitting it. So if I'm calling the direction that the ball was thrown the positive direction, then this change is going to be negative, because that will be a negative force, a force in the opposite direction, right? Ball's coming at you, you hit the ball now in the opposite direction. Okay. I could reverse that. I could say this was negative 5.9 and positive 12. It doesn't matter. Again, it's just your decision of what your reference frame is. Now, the reason why this matters is because for part B, it says, well, what is the final velocity of the ball? Well, the final velocity of the ball is going to be determined by the momentum of the ball. And the momentum of the ball is going to be determined by what momentum it had, which I'm saying is positive 5.9. Add to that now how much we changed that by, and we changed it by negative 12. And so we're going to end up with a new momentum. The momentum of the ball is going to be 5.9 plus that negative 12, which was acted upon it. And so I end up with negative 6.1 kilogram meters per second. That's my new momentum of the ball. And now I can do what we did before, and I could say, well, that momentum is equal to the mass times velocity, and I can find out what 6.1 divided by 1.40 is, and that's going to be about 44 meters per second, or actually I'm going to call that negative 44 meters per second, because the velocity of the ball now is going to be in the opposite direction, back towards the pitcher. So the pitcher threw the ball, gave it momentum of 5.9 kilogram meters per second, and a velocity of 42 meters per second towards the plate. Batter hits the ball in the opposite direction, giving it a change in momentum of -12, which took it from that positive 5.9 to a negative 6.1 and a negative velocity of 44 meters per second. For letter C, it says, well, what force does the ball exert on the bat? Think back to Newton, third law. For every action, equal and opposite reaction. So as the bat was applying 1,320 newtons against the ball was applying 1,320 newtons against the bat. Quick question, why doesn't the bat go flying off into the stands at 44 meters per second? Think about it. The bat has a much larger mass than the ball does. The ball only has a mass of 0.14. The bat would presumably be, I don't know what a bat weighs, Google it, but a kilogram or two, I don't know. I don't play baseball, not since I was like 7. So the point is that because the bat's going to have many times higher mass than the ball does, it's going to have many times lower velocity. Not to mention the fact that the player is still holding on to the bat. But even if they let go the instant that force was being delivered, it's not like the bat just goes flying off. That'd be kind of dangerous, I feel like. All right, last question. A rocket weighing 4.36 times 10 to the 4th newtons. That's its weight. So that's the force of gravity. That's a tricky point. 4.36 E4 newtons. Okay, we'll pull the mass out of that in a second. Has an engine that provides an upward force of 8.90 times 10 to the 5th newtons. That's a big force. 890,000 newtons. And it reaches a maximum speed of 860 meters per second. So a velocity of 860 meters per second. Okay, so let's figure out what we know. First off, because momentum has everything to do with mass, I'm going to go ahead and find the mass. I know that it had a weight of 43,600 newtons. And I know that because weight is equal to mass times 9.8, if I take that weight and I divide it by 9.8, I should be able to find the mass, and I get the mass to be 4.45 e to the third, or 4,450 kilograms. Okay. And now we got to think about this. It asks us to draw a force diagram. So I have that FG down. I have the force up, and that's my force of, I don't know, the engine. We'll call that FE just to give it its own subscript there. And that's going to be our force diagram. I should make sure that this is, it's notably larger. Not to scale this force diagram, but that's okay. So those are the two forces that we're contending with here. For letter B, it says for how long must the engine burn in order for it to reach this speed? For this, we're going to look at the average force being applied, it being equal to the change in momentum over time. The change in momentum we can find. Rockets start at rest. So if this rocket's going to reach a maximum speed of 860, I can find what its momentum is by multiplying its mass by the final velocity, and I get a big number. I get 3.83 times 10 to the 6, so about 3.8 million kilogram meters per second. And that's going to be the change in its momentum, and then I'm going to divide that by the period of time. So we're looking for time. And what that tells us is that we must know the force, and we do. Look at our force diagram. We know that the net force acting on this rocket is equal to that engine force upwards minus the force of gravity. And that's going to be then the leftover force that's able to cause acceleration and cause a change in momentum in this rocket. And so I can do this by taking 8.9 times 10 to the 5th minus 4.36 times 10 to the 4th, and I get a net force here of 8.46 times 10 to the 5th newtons. So that's the amount of force that's causing the change in momentum. And using that amount of force, I should be able to solve for time here. And so if I rearrange this, I can solve for time, and I find that time is going to be therefore equal to the change in momentum divided by that force. So if I know that the change in momentum is 3.83 times 10 to the 6th kilogram meters per second, and I know that the force is 8.46 times 10 to the 5th. I can find that the time for this rocket to reach its maximum speed is about 4.5 seconds, or 4.53 seconds, which is pretty speedy. That's a lot of force. That's kind of an unrealistically low time value, but that's okay. Maybe this is I don't know. It's a pretty powerful rocket. Probably not one with a human strapped to the top, because I imagine if you worked out what the acceleration was, it would be pretty fierce. Okay, so there is impulse and momentum. I hope this is helpful. And if you have questions, please do let us know.